Welcome to science class. Today we are going to introduce the theory of plate tectonics. It'll actually take us 3 videos to cover this. Today our goal is to introduce the idea of plate tectonics, the different types of faults, how plates move about, and what landforms plate tectonics is responsible for. We will also touch on earthquakes. Plate tectonics theory really only came to light in the 1960s. Our friend Alfred Wegener did not have access to this theory, which is a real shame because it would have helped him out a lot. Actually, plate tectonics theory has been invaluable to the scientific community as a whole. One of the great strengths of scientific theories is they unify a broad range of separate observations. This one idea explains why earthquakes occur, and why they are more common in certain places, why mountains exist and why they exist in particular places, why volcanoes exist and why they are also more common in certain places, why those fossils Wegener studied are spread over different landmasses, and much, much more. Let's get started. So I know we are 20 videos into this course, and I am for the first time talking about scientific theory, but it just hasn't been all that necessary until now. In science, a hypothesis is a prediction based off of careful observation and some information gathering. It is taught in places that a hypothesis is an educated guess, which is wrong because a lot of information is gathered ahead of time. A scientist always truly believes their hypothesis will be correct. Experimentation serves the role of ruling out or confirming the hypothesis. Wegener did not just say, yeah, I think Pangea used to exist. And then, oh, what a shocker, look at all this evidence that supports it. It was the other way around. So a hypothesis confirms a particular observation. Great. That observation is then carried out by other people with slightly different parameters to try and prove the hypothesis wrong. That's what no other system does that science does. Scientists try to prove each other wrong. But if a particular observation or mechanism is always confirmed, it graduates to a scientific theory. Theories are well-established, tested, and confirmed facts. Gravity, the germ theory of disease, evolution, general relativity, plate tectonics. These are all true. In the past, when earthquakes occurred or volcanoes erupted, people assumed they were being punished. Well, who wants to live with a down-in-the-dumps worldview like that? It's also arrogant, dangerously so. If you assume nothing bad will happen if you are righteous, then you're not preparing yourself for reality. People literally worshipped volcanoes in the past. Volcanic soil is incredibly rich, as we have covered, so people, I guess in an odd sort of way, understood that the volcano provided for them. As long as they were good, the volcano would protect them. No, it won't. It's literally a pressure bomb. Now, obviously, that line of thinking is not scientific, and while it is based off of observations, they are not logical, sound observations. Now, like I said, scientists try to prove other scientists wrong, not just the ideas we came up with off the tops of our heads. I have here an earth science textbook, copyright 1901. This predates even Alfred Wegener's original paper. In it, they used the best geoscience information they had available to them at the time to try and explain what causes earthquakes. While their explanation is wrong, I applaud their attempt and their application of sound scientific reasoning. Better hypotheses and theories have given us a better explanation of what's happening. At the most basic level, plate tectonics tells us that the Earth's crust and uppermost mantle are a rigid solid body known as the lithosphere. This layer sits on top of and is in motion over a weak, flowing, semi-molten layer called the Asthenosphere. But the lithosphere does not move as a single unit. Instead, the lithosphere is broken into large and small sections called plates, and these plates all have combinations of different motion. Where 2 plates meet is known as a fault. There are 7 major plates and around 8 minor plates. Each of the major plates, except for the Pacific plate, contains most of or all of a continent, plus a large portion of the ocean floor. Some of the minor plates are made entirely of oceanic lithosphere. Others contain sections of continental lithosphere as well. On average, lithospheric plates move around 5 centimeters a year. The energy for this motion comes from the uneven heating within Earth's mantle. Molten material is forced upwards through the lithosphere in areas known as rifts. This molten material wedges apart the plates, and this essentially does all the work of getting those plates to move. Now, Earth obviously isn't expanding like a balloon. If a plate is being pushed by rising molten material on one of its borders, its opposite border is likely doing the opposite and is being plunged back into Earth's mantle to be melted and recycled. Fault boundaries where two plates are being separated are called divergent boundaries. Almost all divergent boundaries are found on the ocean floor, where they have created the mid-ocean ridge. This is an unbroken chain, 65,000 kilometers in length, and it represents where brand new surfaces of our planet are being created. You'll notice that if we slide each continent towards the mid-ocean ridge adjacent to it, this puts the continental puzzle we looked at last week back together. The process of the oceanic lithosphere being created at these rifts is called seafloor spreading. These mid-ocean ridges did not always exist, however. First, Pangaea had to be broken apart. A rift valley is formed from a divergent fault line on land. As the mantle softens and pulls the lithosphere apart, it creates a Great Depression, and volcanoes are common here as well. The East African Rift Valley is about the only place on land today where you find a rift valley. Eventually, the Horn of Africa will be torn away from the continent and become isolated, like Madagascar. Lake Baikal, the largest lake in the world in terms of volume, is a mile deep, and it was created around 30 million years ago when this narrow region of Siberia was being torn apart by tectonic forces. Today, the rift is, I guess you could say, extinct, but the depression it created is still there. Iceland is being pulled apart as the volcanic island nation sits directly on top of the mid-Atlantic ridge. Fault boundaries where two plates are colliding are called convergent boundaries. When this occurs, one plate, or at least a significant portion of it, is driven back into the mantle. We call this process subduction. Convergent boundaries are responsible for all of Earth's mountain ranges and the vast majority of its volcanoes and earthquakes as well. Depending on which type of convergent boundary you have, different features will form. In any case, when two plates collide, there is a huge amount of friction and melting that occurs between the two plates. This friction also generates earthquakes. If you compare the density of earthquake epicenters around Australia versus the mid-Atlantic on this map, you will see there is an enormous difference. This is because along this region in the Pacific, the plates are converging, so there is more tension and more collision. Whereas in the Atlantic, the plates are spreading, so there isn't much tension or collision to speak of. We will touch more on earthquakes at the end here today. When oceanic lithosphere collides with continental lithosphere, a few predictable things will happen. Ocean lithosphere is created by seafloor spreading, where the plate is driven away from the source that created it. This makes oceanic lithosphere nowhere near as thick as the continental lithosphere on average. Oceanic lithosphere is also more dense. This combination of factors leads to essentially the entire oceanic plate being plunged into the mantle when it collides with a continental plate. The top layers of sediment are scraped onto the shore, and any islands that collide with the shore become part of the continental lithosphere as well. That process can be called accretion. This collision thrusts up the continental lithosphere, creating a mountain chain. But because of the massive amounts of friction, buoyant magma rises to the surface where it creates volcanoes. We call these mountain chains, scattered with volcanoes here and there, continental volcanic arcs. The Andes Mountains are a continental volcanic arc system. as is the Cascade Range in North America, where you have the iconic Mount St. Helens, Mount Rainier, Mount Hood, Mount Adams, and Mount Shasta. One volcano in the Andes Mountains, Mount Chimborazo in Ecuador, by a strange quirk can be considered the tallest mountain on Earth. Your homework is to find out why that is. Where two oceanic plates converge, more of the same thing happens. However, because two thin plates are colliding, they don't produce a great volume of land. Instead, they create what's called a volcanic island arc. Well, sometimes it's called that. There may actually be more individual underwater volcanoes than there are ones that break the surface, creating islands. The Aleutian Islands, Japan, Java, Sumatra, Borneo, the Philippines, Papua New Guinea, New Zealand, Tonga, all of these nations and island systems are volcanic island arcs. There's another word for a chain of islands, an archipelago. Not all archipelagos are volcanic island arcs, but most are. When oceanic lithosphere converges, it also creates a trench. A trench is essentially a crease in the Earth's surface. The deepest trench is the Mariana Trench, located halfway between Japan and Papua New Guinea, near the territory of Guam, and it is deeper than Mount Everest is tall. Most of us don't have access to a Mount Everest to look at, but I can explain it to you like this. When you see airplanes extremely high in the sky, the ones that leave contrails behind, and that's contrails, not chemtrails. Their maximum cruising altitude is almost exactly the same as the deepest depth of the Mariana Trench. So imagine where that airplane is the surface of the ocean, and you are standing on the bottom. To be clear, trenches also form just off the coast, where oceanic continental convergence happens. I just wanted to wait until now to bring them up. Finally, there's the collision of two continental plates. Continental-continental convergence creates folded mountain chains. These mountain chains are massive and much taller than other types of mountains. When the plates collide, the upper portion of the lithosphere, which is the crust, does not subduct. Instead, it combines with the crust of the other plate. This is part of what causes the folding you see in these mountain chains. The Himalayas, the Alps, and the Appalachians formed this way. You do not find volcanoes in mountain ranges such as these. Melting does occur, but the crust is simply too thick for that magma to ever reach the surface before crystallizing. The final way plates interact at their boundary is to slide past one another. This is referred to as a transform fault boundary. The vast majority of these boundaries actually occur along mid-ocean ridges. The rate at which sections of the two oceanic plates spread is not uniform, so these breaks occur between them. However, they also occur in other regions. The most well-known fault, probably in the world, the San Andreas Fault, is a transform fault. These boundaries are also called conservative boundaries because no features are created or destroyed. Yet another name for them is a strike-slip fault. Another feature associated with faults, although it's not a physical feature, is earthquakes. Earthquakes are generated at any kind of fault. Earthquakes also occur in places nowhere near major fault lines, but the vast majority do occur directly along the edges of Earth's plates. However, the frequency at which they occur depends on the type of boundary. Convergent boundaries have far more earthquakes and of much greater magnitude. Close to 1 million earthquakes occur every year, but more than half of them are of magnitudes scarcely detectable by people. The really big ones are extremely rare. The magnitude scale used to measure earthquakes is a logarithmic scale. So a 5 is 10 times more energetic than a 4, but an 8 is 10,000 times more energetic. Only 5 magnitude 9 or greater earthquakes have ever been recorded since we've had the technology. The magnitude 9.2 earthquake that hit Alaska in 1964 released more energy than all other earthquakes ever recorded in North America combined. But why do earthquakes happen? The lithosphere is not perfectly rigid as a structure. As plates crash into each other, they deform. This pressure builds until a point very near or directly on the fault slips. The slippage may not be much, maybe 2 to 4 meters, but the whole lithosphere in that region lets go. We're talking the mass of billions of tons of solid Earth, so it's incredibly energetic. This sends vibrations out in all directions. Earthquakes originate typically several kilometers below the surface. The place where the actual movement occurs is called the focus. There are 2 different kinds of seismic waves: body waves and surface waves. Body waves, also called P waves, are compression waves. Pull on a spring and let it go, and you are sending a compression wave through it. P waves have the highest velocity of any seismic wave, but the lowest energy. Surface waves are transverse waves that travel through Earth in an up and down or a side-to-side manner. There are 2 types of surface waves. One is called a shear wave, and the other, for some reason, is also called a surface wave. Surface waves have a lower velocity than P waves, but they carry much more energy. Because of this difference in velocity, you can measure how far away an earthquake began. The velocities of these waves are known, so the gap between them grows at a known rate as well. Simply subtract the difference in time between when your first P wave and your first surface wave arrive, and you can plot a circle that determines how far away the epicenter of the earthquake is. If no fewer than 3 seismic centers make this measurement, their circles will all converge at exactly 1 point. This is how earthquake epicenter maps are made. Next time, we're going to look at the evidence of plate tectonics and discuss how we know for sure that plate tectonics is true. Thanks for watching.